Hey everybody, welcome to the lecture number 4 of the chapter electricity. So before we start with the lecture number 4, let me just recall what all we have done in the lecture number 1, 2 and 3. So in the lecture number 1, we have talked about the basics of electricity chapter, which was about the methods of charging. And we did discuss about the potential difference also, how important it was for the motion of the charged particle. Then in the lecture number 2, we talked about the one of the another important property related to the materials, which is called resistance. So whenever those charged particle comes into the motion, then due to the certain factors, the charged particles are facing resistance or obstruction in their path. So that is measured with the help of resistance, whose formula was rho L over A. And then in the same lecture, we talked about the Ohm's law as well. V is equal to IR, right? Which is connecting the potential and current. Like how much current would flow if we are having this much amount of potential applied to the particular wire. Then after in the lecture number 3, which was a very crucial topic for your CBSE board exam, from where maximum time the questions are coming in the examinations. And at the same time, if you really want to go for JEE or NEET or such kind of competitive examinations, then lecture number 3 was very important for you people because we learned about the circuit diagrams, the series and parallel combinations. Now, what we are going to do in the lecture number 4, for that, first of all, we need to understand what we have missed in the lecture number 3. So in the lecture number 3, the circuits were exactly visible to us that, okay, this will be series, this will be parallel. Sometimes we do not get the circuit which are neither in series nor in parallel. So how to solve such kind of circuit diagrams? For that, we are going to do the lecture number 4. So sometimes the circuits are neither in series nor the resistances are connected in parallel. In that case, how to deal with the circuit theory, how to deal with the circuit diagrams, that is what we are going to discuss now. So what's the topic name? It's as follows. So topic name is Kirchhoff laws and Wheatstone Bridge, and then solving some circuit using some symmetry rules and some other rules using these Kirchhoff laws only. Okay, so without wasting any more time, let us begin with our session and let us learn how to solve those circuit diagrams in which they are neither in series nor in parallel. Okay, so let us begin first of all with the Kirchhoff law. So there are two Kirchhoff laws basically. The simple name is Kirchhoff first law and second law. The Kirchhoff first law can also be called as the Kirchhoff current law. So in short form, sometimes you will find in the books they write KCL, Kirchhoff current law. Now this is going to be very important for you guys if you're going for Olympiads or some other kind of examination, because in Olympiads the questions are coming from the Kirchhoff current law. Now at the same time we are going to discuss about the Kirchhoff second law also, which is the Kirchhoff voltage law. So first of all, let us begin with the Kirchhoff current law, which is KCL. So what does this Kirchhoff current law talks about? It's a very simple, like in general rule, which anybody can understand. It does not require very much previous knowledge and all. See, some simple charge properties would be needed here. You can see here there are four wires, two wires of blue color and two wires of red color. And this is just the junction which has been shown, this point. Okay, so that is just mark for a visual presentation. Otherwise, it's not a very special thing. It's just a junction which is connecting all these four wires. Okay, some current I1 is coming from here, from the first side. And current I2 is also coming. So total current which is reaching at the point, we will call this point as a node, or you can simple language, you can call it as a junction. So this is about the junction only. So how much total current is coming at the junction? I1 plus I2. Now what is the total current leaving from there? So I3 is going. You see the I3 is going out. Then you see I4 is also going out. So total current leaving from the junction is I3 plus I4. So I1 coming, I2 coming, I3 going, I4 going. So total current going is I3 plus I4 and total current coming is I1 plus I2. So now, what is the relation Kirchhoff first law says? Kirchhoff first law says the total current reaching at the junction must be equal to total current leaving from the junction. So I3 plus I4 sum is equal to I1 plus I2. Now this law is basically in accordance with the conservation of charge. Yeah, it's just simple conservation of charge we are applying. Why I'm saying this? Because if the current is flowing, that means there must be some potential difference. So whenever we have the potential difference, charge particle would be in the motion. They cannot be in the rest. They would move. So if the charge particles are moving, that means they cannot sit at a particular place. They cannot accumulate at a particular place. So this junction cannot be accumulated with the charge particle. Let's say 100 charge came from here, 20 came from here. So total charge particle which came here were 120, which means that total charge which is coming would be equal to total charge which is leaving. So this would be, let's say, 40, and this would be automatically 80. It can't be 78. If it is 78, that will say that two charge particles have come to rest here, and that is not possible. So this is not possible. No charge particle will be present here at the junction. No charge cannot be present. So charge cannot accumulate there. If it would be coming, it will go out also. Okay. So that's a simple Kirchhoff first law. So it is in accordance with the conservation of charge. Second law I'm talking about, the Kirchhoff second law. Now Kirchhoff second law talks about, though you can see this is the simple series circuit I have taken for the presentation. Later on, I will also take some complicated cases. Okay. So let us first understand what does Kirchhoff voltage law says. Sorry. So Kirchhoff voltage law is about the potential sum. We know that across every resistor, there is some potential difference. We have done the calculation also. If the current is flowing across any resistor, then V is equal to IR. That is the potential difference across every resistor. For the resistor number 1, V1 is equal to whatever is the current across it multiplied with this with its resistance. Similarly, V2 is equal to I2R2, V3 equal to I3R3. In this way, across every resistor, there would be some potential difference. Otherwise, current cannot flow. You need to have the potential difference across every resistor. Now, what about the Kirchhoff second law? We can also call it a Kirchhoff voltage law. It is about the voltage. The previous one was about the current. In a short form, you will find it is also written as KVL, Kirchhoff voltage law. So KCL and KVL. Now, what does Kirchhoff voltage law says? It says that suppose across this one the voltage is VBC. I'm just writing some symbols here. VBC. Across this resistor the voltage is VCD. Across this resistor voltage is VDE. All right. And this is the battery. So Kirchhoff voltage law say that the sum of potential V plus VDE plus VCD plus VBC would be equal to 0. Sum of all the voltage would be equal to 0. Let me explain you why it is so. Why this potential sum across the entire loop has to be 0. This has a more deeper connection with the conservative forces. We know that there is an electrostatic force. So electrostatic force is a conservative force. If you remember the conservative forces from the grade 9, then the conservative forces tells you that the sum of all the forces in a closed path, work done by a conservative force in a closed path is 0. That's the rule. Work done by the conservative force in a closed path is 0. Suppose if you take example of gravity, then when you take the box upwards, then you need to do the work done minus mgh, because gravity is acting downward, displacement upwards. And when you take the same box downwards, so gravity is acting downwards and displacement is also downwards. So total work done is plus mgh. So total work done, if you see in the closed path, so minus mgh plus mgh, so 0. Similarly, electrostatic force is acting here. That is also conservative in the nature. So work done by this electrostatic force in the closed path would be 0. Because What I'll do, I will move in a closed path, anywhere I can start from. Let's say I start working from here. So I will write down the potential differences across battery, then potential difference across resistor 3, then resistor 2, then resistor 1, and then I come back. So when I come back from there, what I see is that it's a closed path. If it is a closed path, which means that the work done has to be equal to 0, right? Because it's a conservative force. So that's what the meaning is. Means energy cannot be dissipated. Whatever work you will do in going, the same work you will do, you will gain while coming back. Okay. So that's why it is in accordance with the conservation of energy. That's very important. Conservation of energy. So first law was in accordance with the conservation of charges. Charge cannot accumulate anywhere. And second law is in accordance with the conservation of energy. So that is the basic idea about the Kirchhoff second law or Kirchhoff voltage law. Now, let us understand how to use these two laws in the circuit diagrams and how they would help us. So for that, I'll tell you some basic rules as well. And it's going to be very easy. Don't get scared from the complicated diagrams. It will be really easy for you people to understand. Okay. Now, before I go ahead, one application part is there, which is the Wheatstone Bridge. I'll come back to this, right? First, let us make some understanding about the Kirchhoff laws. Then I'll come back to Wheatstone Bridge. It would be easy for you to understand. So let us solve this question. Find out the relation between currents according to the KCL. Let us do this. So where is the junction? That you have to see first of all. So I can see that the junction is at this place. That's the junction point. So at junction point, total current which is coming is I2 plus I3 is also reaching there. I4 is also reaching there. And the total current which is going away from the junction is I1 and I5. So these two will be equal. So that is the answer. It's very simple. And yeah, believe me, even JEE mains have asked such type of questions. So in Olympiads also it can be asked. Very simple thing. Just total sum you have to equate to the outgoing is equal to incoming. Now, before I start with some questions of Kirchhoff laws, which would look like this, let me take you through some of the basic rules. Okay. So let us talk about some basic rules for that. So rule number 1, let's discuss. Just a second. Let me just erase this part. I'll write it here. Okay. Yes. Let us discuss the rule number 1. When you walk in the circuit, because second law, what does it says? Second law talks about the walking around the circuit. Walking around the circuit, what does it mean? We have to write down the potential difference across every element. All right. So dekhiye. Now what we will do, first of all, if I talk about a battery. Now let's say if somebody walks like this, if somebody goes from here to there, A to B. So you see what is happening. This is the higher potential and this is the lower potential. So if somebody goes from A to B, then what he will write for this battery, plus V. What he will write, plus V. Because you're going from the lower to higher potential. So potential would increase. So that's why we are writing plus V. All right. Similarly, if I take another example where if I go from higher to lower. So suppose if I go from higher to lower. So this is the higher potential and this is the lower potential. Now if I walk in this direction, so I explained you when you go from lower to higher potential, you have to write plus V. And when you go from higher to lower potential, true, it will be minus V. Simple. So guys, just remember the simple rule. This would be helpful for you in the grade 12 also. You will see some other circuit elements also like capacitor, inductor. So always it is like that. When you go from lower to higher potential, just write plus in the potential. It will be increment in the potential. And when you go from higher to lower of the potential, it will be minus V. Now let us talk about the case number 3. So battery cases we have taken. There can be only two cases, either lower to higher or higher to lower. Now let us talk about the resistor. So that's the resistor. And let's suppose the current is flowing I in this way. Perfect. So if somebody walks in the direction of current, if you walk in the direction of current, now how I should write the potential difference across the resistor? So what I should write here? V is equal to what? So first of all, I would say that you should think about it. I'm going from uh, point A to point B. Now think about it, whether the potential would increase or it would decrease. What should I write for V? Plus IR or minus IR? Because potential difference would be IR. Now, will it be plus or will it be minus? So always see one thing. You are going in the direction of current. Okay. And how does current flows? From high potential to low potential. So this must be high potential. This must be low potential. That's the rule. All right. Potential always, current always flow from high potential to low potential. So now the thing is, this A must be at the higher potential and B must be at the lower potential. So here I'm going from higher to lower potential. So this case basically higher to lower potential. So minus IR. Now, if I take the case number 4, let's say the current is flowing like this, but I'm walking in the opposite direction. I'm walking like this. So this is A to B I'm going. Now in this case, what should I write for V? So now if the current is going in this way, always mark the higher potential. This is the higher potential. This is the lower potential. All right. Because current goes from high to lower potential. Right. So when you're marking across the resistor, don't look at the battery. Just look at the direction of current which you have taken. Okay. So now B must be the higher, A must be the lower. So now if I try to write down the potential while going from A to B, so what would be written? Plus IR. So when I was walking in the direction of current, I was writing minus IR. And when I walk opposite to the direction of current, I will write plus IR. That's a simple rule. When you walk in the direction of battery, I mean lower to higher, plus V. Opposite is minus V. When you walk in the direction of current, it is minus IR. When you walk opposite to the direction of current, it is plus IR. That's it. So now these 4 simple rules we have to remember. And based on this, now we'll solve 1 or 2 questions based on the KCL and KVL. Let us begin now with the question number 1. So what we have to find out? I will frame the equations for you guys. Rest is your homework. You have to solve these equations using your maths. So here you can see there are 2 batteries, 4.5 volt battery and 3 volt battery. Okay. We have to find out the current across or current through 4.5 volt battery and 3 volt battery. That is the question about. So basically we have to find out the current across the 5 volt battery and 3 volt battery. Let us solve the question. One more thing, which is like very common sense kind of thing. Like if I current is going from the battery, then obviously I would enter also in the battery. So whatever current enters in the battery, that same current goes out of the battery. I have explained this thing to you in the last class also while solving series and parallel. So now we don't know the current value. So let us just assume. Okay. So current would go from higher to lower. So I have taken the direction leftwards. If you take the direction rightwards, it won't be wrong. Automatically in the final answer, you will get the negative sign. So you will understand, okay, whatever direction I have taken, that was wrong. Okay. So this current would go like this. Now this current will reach here, I. Similarly, this current is coming I here. Now here you see the junction. Now at the junction point, the current always divides. So let's say some I1 current goes here. Then what will be the rest current? Because total incoming current should be equal to total outgoing current. So current I was coming, I1 went this way. So I minus I1 will go this way. Simple. 100 rupees. So 20 rupees given to this. So 80 rupees will be given to the right one. Okay. Now the current I minus I1 would be coming here like this. Okay. This I1 will flow here. There is no branching. No branching. And this I1 will reach over here. So finally you see one thing. What is happening at this junction? Let us just verify. So I minus I1 coming from the left side and I1 coming from the top. So total it will accumulate and it will get added from the KCL. It will again become what? I minus I1 plus I1, which is again how much? I only. All right. So now basically, as we can see here, that the normal simple rule is like we have to again start with the basic. The point is current is coming from here and the current is like entering from here, which is I minus I1 and going out and then reaching here as I1. So total current which will be coming here is again I only, because you take the addition of these two, I minus I1 plus I1, which is again I only. All right. Now let us begin. Now let us begin with the Kirchhoff voltage law. How to apply the Kirchhoff voltage law? So first of all, you guys see one thing. There are two variables. I don't know the value of I and I don't know the value of I1. Both are unknown for me. So I need two equations to solve them. Correct? I don't know value of I don't know value of I1. So I need two equations to solve them. Now, how I would be solving them? That is a very good and very important question. So for that, I'll write the Kirchhoff voltage law. Kirchhoff current law we have used at the junctions. So now I will walk across the circuit. Okay. So I will walk across two loops so that I get two equations. If I need three equations, I'll walk across three loops. So let us identify what loops we can walk. And there is no as such rule that you have to select this loop only. It's always your choice which loop you want to walk across. Yeah, it should be a closed one. So let's just suppose somebody starts from here, then goes to B, then goes to C, then D, then E, and then coming back to A. So basically starting from A, then B, C, D, E, and I have come back to A. Okay. So this is the entire loop we have taken here. Now, let us start walking. So let's go from A to B first of all. So I'm going this way, guys. So what should I write? Plus, because lower to higher. So plus 4.5. Then I'm going from B to C. It's a plain wire, so no potential difference there. Okay. No resistance. Then from C to D. From C to D, the current is how much? It's I we have taken. And I'm walking in the direction of current. So just remember these rules. If you're walking in the direction of current, take minus IR. So minus 3 multiplied I, because current is I here. Then you go from D to E. That's a loop for you. So now again, you're walking in the direction of current. So minus IR. Here the current is I minus I1 and resistance is 6. And then you go from E to A. No potential difference because it's a plain wire. So you started from A and you came back to A. Total sum will be 0. All right, from Kirchhoff voltage law. So let us just simplify this equation, 4.5, or let us make it even more simple. I can write it as 9 by 2 minus 3I minus 6I plus 6I1 equal to 0. All right. And what else I can do here? 9 by 2 minus 9i. Tell me if I'm making any mistake. Okay, you can tell yourself while while watching this lecture. 9 by 2 minus 9i plus 6i. Okay, plus 6i1 is equal to 0. Okay, now we can do some simplification. This will become 3 by 2 minus 3i plus 2i1 equal to 0. So 3 is equal to 6i minus 4i1. Equation number 1. You can just check it once again if there is any calculation mistake. 3, 6 and 4. Yeah, that's correct. Okay. Now the equation number 1 we have got. After this, what we will do, we will need one more equation. So for that, I'll go to the loop number 2. I guess most of you are thinking of a upper loop. That's a very small loop. So E, you can see here, that's the E. This point is D. So DE, and then you can see this point we can mark as F, and then G. So loop number 2, I will take it as loop number 2, D, E, F, G, D. Let me just check it. D, E, F, G, D. Yeah. So I'll start from D. I'll come back to D. That's the rule. Let us start from D. So first of all, when you go from D to E, I minus I1 current, you are walking in the direction of current. Any direction you can walk. That is your choice, guys. I'm again repeating. It's not a hard and fast rule that whatever I have taken, you should do that only. Now I minus I1 multiplied 6, but with a negative sign because I'm working in the direction of current is equal to, then from E to F, no current. No potential difference. F to next point, G. You see two things. Achha, battery's potential difference, for that you don't need to you don't need to look at the current direction. Current direction you have to see only for resistance. So you are walking from lower of the battery, from F to the higher of the battery. So we will just write plus 3 only. So we will just write here plus 3. Next is, you are walking across the 10 ohm resistor, but in the opposite direction. So I must write plus 10 multiplied, the current value is I1, which is equal to 0. Now you can see, let us just simplify this. So 6 I1 plus 6I. Oh, sorry. I guess I have made some mistake here. It was I minus I1. Yeah. So minus 6I plus 6I1 plus 3 plus 10I1. Now minus 6I1 plus 10I1 is nothing but 16I1 plus 3 equal to 0. So now from here, what will be getting? Minus 6I, and this is 16I1 is equal to minus 3. Or you can write it as in a better way. 6I minus 16I1 is equal to plus 3. That is the equation number 2. And if you look at the equation number 1, it was 6I minus 4I1 equal to 3. So 6I minus 4I1 equal to 3. That was the equation number 1. Let us just subtract these two equations. So when we'll subtract these two equations, I mean equation 2, I am subtracting from equation 1. That's what I'm doing. So when I do that, what I'll be getting? is plus 4i1 minus 16i1, which is minus 12i1. And that is giving me the answer equal to 0. Just check it once again if there is any mistake we have made. Yeah, I guess everything is correct. Otherwise, you guys can check the rules we have written correctly. All right. And the rest thing calculation part I'm leaving for you guys. Okay. So anyways, I'm solving it. So it is coming out to be 0 current because 3 minus 3 is 0. 6 minus 6 is 0. So I1 we'll get as 0. Now we'll put this value of I1 equal to 0 in the equation number 1 or 2 anywhere. Let's put in the equation number 2. So 6i minus 0 is equal to 3. So I is equal to half ampere. And I1 equal to 0 ampere. Let us go back. So our question was current through the 4.5 volt battery, half ampere. Current through the another battery, 0 ampere. Okay. Okay. So that's the main thing. All right. Now let us, if somebody asks us what is the potential difference across 3 ohm. So what we will say that the current is half, resistance is 3. So 0.5 volt, V is equal to IR. Okay. That's the way to solve the Kirchhoff voltage law questions. Okay. I'm going to take one more question, which is based on the, again, Kirchhoff current and Kirchhoff voltage law. So let us begin with this question also. All right. Again, if you have understood the Kirchhoff current law and voltage law in a good way, whatever rules I told you, then try to do this question first of all yourself. Stop the video here and then come back and see the equations which I have written, whether that is matching with you or not. Okay, so here it has in the question itself, they have given the current branching. Okay, so this is the I1 value. The question is again same. We have to find out the value of I1, I2. I1 is this current, and then this current is going out to I2 in this branch. This arrow must be opposite. Okay, so basically, no, correct only. They have given the right arrow, correct. They have taken the opposite one. So actually, this I1 current they have taken like this. So this is the junction T. At the junction T, the current I1 is coming this way. And the current I2 is going this way. I1 plus I2. And current I2 is coming from this side. You see this? This is I2 current. So it would be flowing like this basically. All right. So guys, basically if you see carefully, then you will find that I1 and I2 are approaching at the junction T. So they will combine and they'll go back as I1 plus I2. Now let us do the KVL calculations. So let me start working across the loops. I have to take 2 loops because I have 2 unknowns here, I1 and I2. So first of all, I think I can take one loop as Q. I start from Q, then P, K, T, Q. Loop number 1. Let's start working. So when you start from Q, first of all, battery plus 4. This way I'm going clockwise. P to K. Oh, sorry. After battery, we have taken the current as I1. So minus 4 I1. Across it, along the direction of current. Then from P to K, nothing. From K to T, minus 2 I1. Let's go from T to Q, minus 3 times of IR. Current is I1 plus I2. And sum is equal to 0. Let us just simplify this. 4 minus 4 I1. This is 6 I1 will become. All right. And then minus 3 I1 minus 3 I2 equal to 0. So 4 minus 9 I1 minus 3I2 equal to 0. Just see if there is any mistake we have made. I guess everything is correct we have written here. Yeah. So now what I'll write, 9I1 plus 3I2 is equal to 0, is equal to 4. Equation number 1. Now we can go to the loop number 2. Loop number 2 I'll take as this. I'll start from R, I'll go to S, I'll go to T, I'll go back to Q. R, S, T, Q, and coming back to R. So now let us start from R to S, nothing. S to T, I2 current. So minus 4I2 in the direction of current. Then T to Q. T to Q is minus 3 times of I1 plus I2 because in the direction of current again. Then Q to R. So first of all battery, but going from lower to higher, higher to lower. So going towards negative. So minus 6. And then across the resistor. So current is I2 like this. See this, the current I2 going this way. So this current would be I2 only across 2 ohms. So minus 2I2 equal to 0. Let us just simplify this also. Minus 4I2 minus 2I2 minus 6I2. Minus 6I2 minus 3I2 minus 9I2. Okay. And I can write it as I1 minus 3I2 is equal to 2. Equation number 2. All right. Now, let us write down these two equations. We have got the two equations. Now we will have to solve them. Equation 1 and equation number 2 is I minus I1 minus 3I2 is equal to 2. Now we have to solve them. Just check if there is any calculation mistake because I guess I have done everything correct. There is a very good probability that we can make some calculation mistake here. So I'm going very slowly. Now I will just add these two equations. Operation is 1 plus 2. I'll be adding them. So when I add these two equations, see guys what I'll be getting. 9I1 minus I1, 8I1. Addition of these two will make it 0. 6. So I1 is equal to 3 by 4 ampere. And now you know what to do. The next, put I1 in the equation number 2. So minus 3 by 4 minus 3I2 is equal to 2. So 3I2 is equal to minus 2 minus 3 by 4, which would give you I2 equal to minus 11 divided by 12 ampere. Now what is this minus sign representing here? This minus sign is representing that this direction was wrong. So there is no problem. Even though we have taken the wrong direction, our final answer is telling us that the minus sign is coming if our calculations are correct. That means the current will be flowing this way. but you have assumed it to be this way, so that's why we are getting a negative sign. So don't worry about it, that in which direction should I take the current. Anywhere randomly you take the current, ultimately your final answer would give you the explanation, okay, you must take this one only. So that's it, guys. Now we have understood how to use KCL and KVL. And always remember, loop choice is yours, walking direction is yours, current taking direction is yours. So everything you have to decide, and whatever you want, you decide. Don't need to make any stress, don't need to take any stress that which one should I take. Randomly you take and start solving the circuit. Ultimately, you'll get the same answers only. So don't worry about it. Now let me go back to that discussion which I left, the Wheatstone Bridge. Now with this Wheatstone Bridge is basically a very special case. This is a experiment basically. A special case I'm saying because some amazing thing would happen here. So what is that amazing thing happening? Let us just have a look. You guys can take it as a homework for you people, okay? And you can easily prove it, that why this equation is written at the point of balance or something. You will be doing the experiment of this in the grade 12. Okay, it comes under the current electricity chapter, Wheatstone Bridge. It's a part of this electricity part chapter only. What is the question? What is this Wheatstone Bridge is about? You can see here we have this entire circuit connected like this. So current would start from here. So if you take current I coming going out from the battery, then current I must enter. We know this simple rule. Now current I would reach here. So that current will get divided. Some current will go here and some current will go here. Now this I1 current is coming like this, and this I2 current is coming like this. All right. So basically I got divided into two parts, I1 plus I2. All right. So now guys, the thing is this I1 current coming this way and I2 coming out, I2 current is going this way, coming this way. So guys, see one thing. When this ratio R1 over R3, this resistance and this resistance, this ratio is equal to, just a second, yeah, R1 over R3 is equal to R2 over Rx. Rx we don't know, it's an unknown value. All right, so R1 over R3 means these two ratio is equal to these two ratio. If this is happening, if this is the condition in the question, if this is how the values are given in the question, then what you guys can do, you can just take this middle branch having current 0. So current through the galvanometer will be 0. Galvanometer is a device which will show you the deflection. All right. So basically, when this condition is valid, that R1 over R3 is equal to R2 over Rx. When this condition is valid, in that condition, current through the middle branch, the galvanometer branch will be 0. Not through the branch which is connected to the battery. Sometimes students get confused about that. That they make the current 0 across this one, because sometimes they'll show you the battery like this way. All right, so do not get confused with that. Across battery branch, the current won't be 0. Current would be 0 around the galvanometer branch, the another branch where the battery is not connected. So basically, the condition must be true. This two ratio must be equal to this two ratio. So cross this one, current will be 0. So what will be the advantage of that? Let me show you one with one numerical. Just a second. Let's see if we have space there. Yeah, I can make one numerical here. Suppose we have got a circuit like this. Okay. So that is a circuit given to us. The question is find out the current through the battery. Current through the battery means basically this current. So guys, see one thing. Now this branch is connected from here. From here, it is connected with the battery. Now you can see only this part of circuit is there. So this ratio 10 over 20, half. 40 over 80, half. Means this two ratio is equal to this two ratio. Means it's a Wheatstone bridge. If it is a Wheatstone bridge, then this branch would not be having any current. So if this branch is not having any current, what you can do? You can simply remove it. So let us just draw the new circuit. And you would find that is very beautiful and simple circuit, which you have solved multiple times. 10, 40, 20, and 80. These are ohm resistance. 20 volt. Why did I remove the middle branch? Because across the middle branch, current would be 0, means the potential V is equal to IR, V is equal to 0. So no need to worry about that branch. Just remove it from there. So guys, what will happen now? 10 plus 40, 50, 20 plus 80, 100. So what is the new circuit we are getting? New circuit we are getting as 50, 100, and there is a battery here, 20. Now 50 plus 100, what is the value of equivalent resistance? 1 by 50 plus 1 by 100. So I do not have space here. So you can do that calculation. 1 by 50 plus 1 by 100. So that I can write as 3 by 100 after taking the LCM. All right. So this will become 100 over 3. Means total equivalent resistance is 100 by 3 ohm. It's just a parallel combination now. So what is the value of current? It would be V by R. So 20 by 100 by 3. So which will give us the current value as 3 by 5 ampere. Okay. So pardon me if I have made any calculation mistake. I think I have done everything correct. Rest you can check also. Once cross verify you can do. So that's all the idea about the Kirchhoff voltage law, Kirchhoff current law, and the Wheatstone bridge. So basically always remember the 4 rules which I have told you. Battery working does not depend upon the direction of current. Resistance will potential difference across the resistor will be decided by the direction of current and the way you walk. Those are the only simple rules, and you will get the answer of every question, any complicated circuit you want to solve. All right. So now you have also learned something extra apart from the series parallel. So this complicated circuit might not be asked in your CBSE exam, but may be useful for your Olympiads and as a foundation for JEE and medical and KVPY examinations. So guys, that's all from my side. Thank you so much. If you have any further doubt, just put it on the PDF. Thank you so much. All the best.